average value of a function and mean value theorem for integrals. Let's start with a bit of review. Find the average of the two numbers 10 and 20. So let's go through the process. We add the two numbers and divide by 2. So 10 plus 20 is 30, and 30 divided by 2 is 15. I'm sure we didn't actually have to show the work for that, but we just want to think about the process. We added the two numbers and divided by 2 because that's how many numbers we added together. In general, if we have a finite collection of values, a1, a2 to an, to find the average or the mean, we use the formula a1 plus a2 all the way to an all over n, the number of terms we added. But now, what if we want to find the average of an infinite collection of numbers, specifically all the values of a continuous function over a given interval? So here's a nice example. Suppose f of t represents temperature as a function of time. Then f of t is a continuous function, and we might wish to consider the average temperature over a period of time. So for example, here we have a continuous function that might represent temperature. So let's say the temperature starts at 60 degrees Fahrenheit and then increases over a period of time. Let's say this is in hours, and then starts to decrease a little bit. So we have a continuous function, an infinite collection of numbers, and we want to find the average of those values. Well, that brings us to the following formula. To find the average value of a function f of x, the average value of an integrable function f of x on an interval from a to b that is closed, it is given by the formula f av for average is equal to 1 over b minus a, the integral from a to b of f of x dx. So I really think this version helps us understand how it connects to a finite collection of values. Remember that integrals add up, and so we're adding up all of the values from a to b on the function f of x dx, and then we're dividing by the total number of values between a and b. So to find the total number of values, or essentially the distance, we subtract b minus a. So it's the same idea. We're adding up all those values and dividing by the total number of values. This version just allows us to think about 1 over b minus a in the front. And note, average value is also referred to as mean value. So average and mean are used interchangeably. Let's jump to an example. We'll find the average value of the function f of x equals natural log x over x on the definite interval from 1 to 5. So the average value f av is 1 over b minus a. So we're going to have 5 minus 1. The integral from 1 to 5 of our function natural log over x dx. All right, so we have 1 over 4, the integral from 1 to 5 of natural log of x dx. This definite integral can be solved with u-substitution, so I can go ahead and let u equal natural log x, then du is 1 over x dx, which is perfect. Let's change our limits of integration from x's to u's, so we'll have u of 1, natural log of 1 is 0, u of 5, natural log of 5 is just natural log of 5, we'll leave it like that. So our integral becomes 1/4, the integral from 0 to natural log 5 of just u du, since natural log x got replaced with u, and then 1 over x dx got replaced with du. Now, we don't have to return to x's anymore. We can just evaluate this using the fundamental theorem of calculus. So we'll have u squared over 2, evaluated from 0 to natural log 5. We'll leave that 1/4 in front. If I substitute in natural log 5, I have natural log of 5 squared over 2, and then minus 0 squared over 2. So that's just 0. So we'll leave our answer as 1/8, and then natural log of 5 quantity squared. In this example, we're told the average value of f of x equals 3x squared plus 8x on the interval from 0 to b is 12. Find the value of b. So this one's really interesting. So we have our value of a is 0, but we're trying to find the value of b. And we've been told the average value is 12. So let's go ahead and set up what we know. So the average value is 12. So 12 is equal to 1 over b minus a. Well, that's just b minus 0. So 1 over b, the integral from 0 to b of f of x dx, 3x squared plus 8x dx. So we want to work through this and solve for b. So I have 12 is equal to 1 over b, and now we'll take the antiderivative of 3x squared plus 8x. So that's going to go ahead and give us x cubed plus 4x squared, evaluated from 0 to b. So we're just kind of doing the power rule on each of these terms for integrals, and then we're going to substitute in b and substitute in 0. So we have 12 equals 1 over b. Then we'll have b cubed plus 4b squared, and then minus, well, if I plug in 0 to these x's in the polynomial, that's going to be gone, so we really just have those two terms. Now, let's distribute in the 1 over b. That'll be nice. Then we'll just have b squared plus 4b. And now we have a quadratic equation, which we must set equal to 0. So we don't want to do something weird, like factor out a b and set each term equal to 12, which a lot of people do. I want to set this equal to 0 by subtracting the 12 to the other side. So b squared plus 4b minus 12 equals 0, so that I could use the zero product property. I'm going to factor this guy. He's going to factor to b plus 6 and then b minus 2 equals 0. So I get two values for b. If I set each factor equal to 0, I'll get b equals negative 6 and b equals positive 2. So, is it both values? Well, if I look, I'm told that the interval is from 0 to b. We wouldn't put a negative number after 0. So we're going to choose the positive value for b, which is 2. Now let's find the average value of f on the interval from 0 to 4, but f is presented to us in graphical form. Let's write out the formula. So f average is 1 over 4 minus 0, so 1 over 4, the integral from 0 to 4 of f of x dx. Now to evaluate this definite integral, we're going to have to use the idea of the definite integral representing the signed area between f of x and the x-axis here. So here is the area that we are trying to find roughly, and we're going to do that using geometry formulas because there's nice geometric shapes that are created. So this first shape here between 0 and 1 is a triangle. So we have 1/2, base 1, and height 2. So 1/2 times 1 times 2 is 1. So this triangle has an area of 1. And then let's actually notice that each of these individual squares has an area of 1. So basically we have 1, 1, 1, 1. And then these two triangles combined would form one square. And so that's a total of 1 altogether right there. So this is like 1/2 and 1/2. So altogether, I have 1, 2, 3, 4, 5, 6 as the total area. So I have 1/4 times 6, which simplifies to 3 over 2. Now let's see what the mean value theorem for integrals tells us. If f of x is continuous on the closed interval from a to b, then there exists a value c in that closed interval such that f of c is equal to the average value, 1 over b minus a, the integral from a to b of f of x dx. Or here's another way to write it. The integral from a to b of f of x dx is equal to f of c times b minus a. So we're taking this b minus a and multiplying it to the other side. And again, notice this top line, f of c equals f average, right? That's what we're saying. There's some value c such that it equals the average value. So now I want to try to understand what this means on a graph. Here's a continuous function on a to b. So this theorem is saying there's some value c in a to b such that f of c equals the average value. But I'm going to focus on this version here. So there's a value c such that the integral from a to b of f of x dx, so what is that? That's the area underneath f of x between a and b. So there's this value c such that the area is equal to f of c times the quantity b minus a. So I'm going to show you what this represents. This represents the area of a particular rectangle. So I'm going to sketch that rectangle. So I'm going to go ahead and approximate a value of c here. I'm going to explain why I picked that. It might be a little bit off. So here's f of c. If I plug in c, I get f of c. So b minus a is this distance here. And then f of c is now a height. So here is a height. So what this creates is a rectangle. So the area of this rectangle is base times height. The base is b minus a, and the height is f of c. And that's exactly what this is here. So this is base times height. So let's kind of think about it again. There is a value c such that there is a corresponding height f of c that's going to be the height of a rectangle, where when I multiply f of c times b minus a, that rectangle has the exact same area as the area between the function and the x-axis on the interval from a to b. So this rectangle is close, but not perfect. So I can see there's like a little bit of over area here, and then I'm missing some area here. So I probably need to slide c over a little bit to get that actual value of c that meets this. But hopefully you can understand the idea that c does exist. There is a value of c so that the height at c would be the height of the rectangle, and then we'd have the base from a to b. When I multiply that base and height, that area is the exact same area as the area under the curve f of x from a to b. Let's look at a full example here where we walk through sort of each step. So suppose f of x equals the quantity x minus 3 squared. Find the average value of f of x on the interval from 2 to 5. So we're just finding average value. F av is 1 over 5 minus 2, so 1 over 3. The integral from 2 to 5 of x minus 3 squared dx. Now we could absolutely expand this out and just do the power rule, but I'm actually going to do a u-substitution on this. So I'm going to let u equal x minus 3, then du is dx. We'll change our limits of integration to u's. U of 2 minus 3 is negative 1. U of 5 minus 3 is 2. And so our integral is going to become the integral 1/3, the integral from negative 1 to 2 of u squared du. And so now I have 1/3, we'll have u cubed over 3 evaluated from negative 1 to 2. So I'll leave out the 1/3. I'll have 2 cubed over 3, that's 8 over 3, minus negative 1 cubed over 3, that's negative 1/3. 8/3 minus negative 1/3, that's 9/3. And 9/3 is 3. So I have 1/3 times 3, which is just 1. So my average value is 1. Now let's move on to part B. We want to find the value of c in the interval from 2 to 5 such that f of c is the average value of f of x on 2 to 5. So we're basically trying to solve for c using the fact that f of c has to equal f average. right? So we're trying to find that value of c. So f of c simply means plugging c into the x in the f of x function. So we're going to set up the equation as c minus 3 squared is equal to f average, which we just computed in the previous part to be 1. So now let's go ahead and solve for c. If I take the square root of both sides, I'm going to get c minus 3 is equal to plus or minus 1. And so if I add the 3 to the other side, I'm going to get two different values. I'm going to get 3 plus 1, which is 4, and then I'm going to get 3 minus 1, which is 2. Well, the mean value theorem says there is at least one value for c, but there can be two. And so let's kind of talk about why both values do work. Because in part C, we're going to sketch the graph of a rectangle whose area is the same as the area under the graph of f. So the area under the graph of f from 2 to 5, let's sketch that. So we have the area under the graph from 2 to 5. It's going to be this area here. And then what the mean value theorem told us is that there's two values, 2 and 4. So 2 is right here. So if I construct a rectangle, the input being 2, the output happens to be 1, so that's f of c. So that rectangle with a height of 1 and then a base that extends from 2 to 5, it turns out that rectangle has the same area as the area under the curve from 2 to 5. And I just want us to notice that when we plug in 4, it's the same output of 1. That f of c value happens twice. So that's why both 2 and 4 work as values that satisfy that mean value theorem for integrals.